G'day, g'day. Today, guys, what we're going to do is going to talk a little bit about the circumstellar habitable zone. Basically, what the circumstellar habitable zone is the distance between water boiling around a star and water freezing around a star. So, here, with my exceptionally well-drawn little notepad gizmo, we're going to explore this in a little bit more depth. So, here, we have what it means to be habitable. Now, basically, when we say habitable, we're referring to a few different features. So, critically, elements that are essential to life. So that's carbon, hydrogen, oxygen, nitrogen. These are like the building blocks in terms of what's going to create life forms, in all sorts of different avenues, in terms of like hydrocarbons and all that sort of jazz, which are essential to life. Secondly, that we have a liquid solvent. Particularly interested in water for a couple of major reasons. So, the first being that it's an excellent solvent, and the most important probably is the the change in temperature related to when the water is freezing and when the water is boiling. So the difference is 100 degrees Celsius, right? And we have other examples of solvents that would be ideal, but in the case of ammonia, methane, and ethane, they're all good solvents as well, but the energy related with them while they're at liquid temperature are much, much lower. And so in terms of prospect of developing life, they exist at such a way where because they are such lower energy, it takes a much longer period of time for life to emerge, while relating with these solvents. The third is that, the energy source, right? So as I sort of briefly alluded to earlier, an energy source is obviously going to be the star that the actual planets are going to be neighbouring. So provided we have good circumstances for this star, it will be more or less likely to develop life. As illustrated in workshops previous to the one we concentrate on the habitable zone, we realised that between 0.4 and 2 solar masses would be ideal. The reason for this is being that a much more massive star would be too short of a lifespan, while a lower mass star would produce much less energy, and then therefore to be closer to the habitable zone would be to be tidally locked. So obviously that's not very ideal sort of circumstance. So basically, when you take this sort of thing into account, where we have this sort of range in stars, we can sort of make a judgment about whether or not we're even going to investigate the habitable zone of a star based on its mass. So this part here, so the stable climate, right? So in terms of how this planet is going to go, revolving around this star, will determine a couple of different things. So probably the most important one in terms of stability for climate is going to be the planet's eccentricity, which is basically where it's going to be either quite a large ellipse where it's got a wide sort of circular spread where the radius is much greater, much more different in different areas, or being perfectly circular. And ideally, we'd have a perfect circle in this case. Now, so if this is my little diagram of a habitable zone. If in this case, right, we're sitting in this habitable zone here, and we're closing around nice and easy in a pretty clear circle, right? If this orbit is now much more eccentric, it comes out and around all the way around outside the habitable zone, comes back in, and then dwells right back around again. So if this is a more realistic orbit, if we have an eccentric sort of behaviour, we can see that it's going to go in and out of the habitable zone, wherein it'll be going through drastic changes in temperature. We'll have like an ice age and back to normal in a matter of however long the planet orbits the star. So it could be 50 years, or as an example of orbiting the star, like 50 Earth years. But in that 50 years, it's going to go through such a drastic change that life will never be realistically supportable. So, based on this information, then we've got a pretty pretty large bit of stuff to sort of deal with, right? So, to sort of work out how we're going to go about this, right? So, in order to determine where the actual amount of light will be, or the amount of sufficient light will be from these couple of major formulas, right? But they're based on a couple of assumptions, right? They're probably the most important things that are going to contribute to the way the habitable zone will work will be like the presence of an atmosphere or absence in some cases. The composition of that atmosphere will drastically change it. So if it's carbon dioxide dense, it'll retain more energy, that sort of thing. The rotation of the planet, so that's coming back into the eccentricity, the albedo of a planet, which is basically how much the planet reflects light. So for instance, if you have like a very flat planet, it's likely that it'll behave more as a mirror. If it's highly metallistic, then it will reflect more light than, say, something that's just mountainous and clumpy. Sort of much like a mirror versus a rock. A rock's able to absorb more heat, whereas a mirror will reflect it. The obliquity of the planet, which is the tilt angle the planet basically exists around, that'll determine how drastic the change is in terms of like its seasons and that sort of thing. And also, as we said earlier, the eccentricity. So the assumptions for these formulas, right, are basically that we have an albedo of 0, the planet has no atmosphere, and radiation absorbed onto the planet is distributed evenly across the whole surface, and the planet has a perfect circular orbit. So bearing that in mind then, if we look at the flux is equal to the luminosity of the star divided by 4 pi d squared, which is going to be the surface area of the sphere, and we have that in combination with the flux is equal to Stefan-Boltzmann constant times temperature to the power of 4, where the Stefan-Boltzmann constant is this here. If we substitute for F and solve for D, we find this is our formula. So basically what we'll do is if we'll find the luminosity of our star that we're looking at in question, and make assumptions about the temperature, we can infer then how wide or however what the distance will be. So we'll compare the two major distances, wherein we have the temperature of water when it's boiling at 100 degrees Celsius, so that'd be 373 degrees Kelvin, and water when it's frozen, which would be 273 degrees Kelvin. And then basically compare that distance, and you'll know exactly how far the habitable zone is in terms of the radius of the orbit. And that's my little demonstration on habitable zones. Hope you've enjoyed it.